Hi, imagine you're designing a model that brings blood flow to life, literally, because that was our challenge. In this project, we built a simple and low cost model to show two different types of blood flow. One in a healthy artery where blood moves smoothly, also known as laminar flow, and the other with an aneurysm where blood moves in a messy way, which is known as turbulent flow. The main goal was to build a safe and realistic ultrasound phantom. This model needed to show both normal flow and an aneurysm like flow, so it could be used for training or testing with ultrasound. So, first we had to choose and prepare materials that act like human real tissue. And then we tested if these materials worked well with Doppler ultrasound to show the blood flow clearly.
For the selection of materials, we use gelatin to represent soft tissue because it is cheap and has a similar texture to the body. We mix 30 grams of gelatin with 1 cup of water to make it firm and clear for the ultrasound. We added glycerin to make it a bit stronger and vinegar to help with the texture. To simulate the blood vessels, we used plastic tubes and we made 3D printed plastic base to hold everything together. We also checked how well the sound travels through the materials. This is called acoustic impedance and helps the ultrasound image look more like what we see in the real body tissues. The values for this is gelatin 1.5 millirays and glycerin 2.0 millirays.
Okay, so how we built the Phantom. First, we designed and 3D printed the base mold. Then we placed the tubing in the mold to simulate the arteries. And then we made the preparation of the gelatin based mixture, which was formed by gelatin. We used 30 grams of unflavored gelatin, and we dissolved this in a dissolution temperature of approximately 60 degrees Celsius in 240 milliliters of water. So we could obtain a final gelatin thickness of approximately 2.5 centimeters, and we filled this mold with this 3D printed mold with this mixture. Then we did the embedding of the aneurysmal dilation and sealing. And some of the challenge we faced while doing the Phantom was avoiding air bubbles, making the correct positioning of the tubing, and prevent leaks while the water was flowing. For this project, we used a Siemens Acuson Redwood ultrasound machine. We used two modes, the color Doppler mode and the B mode. We used a linear transducer in order to see our phantom. In the healthy vessel, the blood flow was smooth and in one direction. We saw clear red and blue colors, which mean that we had laminar flow in the tubes, while in the aneurysm the flow was different because the colors were more blue than red. This shows that we had turbulent flow, and we used the color bar to estimate the speed. And based on similar studies and based on literature, we have that a healthy vessel flows at a range of 10 and 18 centimeters per second, and an aneurysma uh, flows within a range of 5 to 10 centimeters per second.
Okay, now in this slide, we can see how blood moves inside our model using Doppler ultrasound. The first image shows a normal flow inside a healthy artery. The colors are uniform, mostly red and blue, and they move in one direction. This is called laminar flow. In the second image, we can see a coronal view, which gives us a frontal view of the vessels. Here we start to see more color changes, which tells us the flow is getting more complex. And maybe it's due to a change in the vessel shape. Now we look at the blood flow in the aneurysm. In the first image, called aneurysm flow, we see the blood is entering and leaving the aneurysm. Before the aneurysm, the flow is smooth and normal, but after it leaves, the blood gets a little bit faster, but the flow is still messy and not fully stable. In the second image, approaching the aneurysm in the coronal view, we are looking inside the aneurysm. Here, the colors are mixed and moving in many directions. This shows turbulent flow because the vessel is wider and the blood moves slowly and chaotic. In the third image, the normal flow again, we see the blood before and after the aneurysm. This confirms that that the flow becomes slower and chaotic inside, and then slightly faster when leaving, but is still not organized. This happens because the vessel gets wide, so blood slows down and then narrows again, which makes the speed increase a little bit, but the flow stays turbulent.
Furthermore, between the construction methodology, we face some challenges. During the process, we face the removing or air bubbles from the gelatin mixture. Uh, we're maintaining the tube in place during setting and preventing leaks of the gelatin once the structure is complete. Now moving to the fluidic system, we utilize NKP peristaltic pump, which operates with DC brush motor available in 6 volts, 12 volts, and 24 volts configuration and consumes about 5 watts of power. The flow rate is adjustable, ranging from 10 to 60 millimeters per minute, which allow us to simulate different hemodynamic conditions. In terms of pulsating control, the pump's three-rotor design provides a modern level of pulsate flow, which is important for Doppler ultrasound evaluation. This setup allows us to realistic simulate vascular flow and structural condition for ultrasound-based analysis, especially in pathologies such as aneurysm.
To wrap up, I would like to highlight the main conclusion of our work. First, the phantom we developed successfully replicate key hemodynamic differences between normal vessel and one with aneurysm as observed in Doppler ultrasound imaging. Second, our model accurately reproduced important flow patterns such as laminar and turbulent flow velocity profiles, and waveform distortions. These phenomena closely match those seen in the real clinic settings, validating the phantom's potential for training and experience purpose. Third, the system provides to be cost-effective and reproducible, making it a practical solution for simulating vascular pathologies in a visual and educational manner. And finally, despite some structural limitations such as potential leak or tubing misalignment, the Phantom serves as a solid foundation for future improvement. It has strong potential for teaching applications in biomedical engineering and ultrasound-based diagnostics.